Welcome everybody. It's Ramchandra from Civil MECH Maths Concepts channel. Till now, in structural analysis, 20 videos are released and it is the 21st video. Till now, I have taken up cantilever beam and simply supported beam. Today, I will be talking about the overhang. A simply supported beam is extended by a overhang. It's one of the most important engineering applications. Then I have taken up this overhang. Let us try to analyze this overhang and see how the shear force and bending moments are calculated, and also the deflections are calculated, and also how the behavior of the curves, shear force diagram, bending moment diagram and deflection curves are drawn, and we will dwell into the lecture now. And it's a overhang, and this is a pin joint, this is a roller joint, it's a free end. As part of the structural analysis, supports are concerned. I have already discussed in the last lecture about the supports and their properties. As far as pin joint is concerned, slope is not equal to 0, but delta is equal to 0. At roller joint, slope is not equal to 0, but deflection is 0. At free end, deflection and slope are present. In a fixed end, deflection and rotation both are absent. Now, for details of this, you can refer to my previous lecture. It's Ramchandra again. It's a very important lecture. In between, I will be giving the tips for answering the multi-choice questions, that MCQs also, so that you view this lecture till the end. Otherwise, you may miss some important MCQ tips for answering in the examinations like GATE SSC JE, GATE SSC JE, and engineering, UPSC engineering services examination. And for these examinations, deflections of the beams, shear force diagram, bending moment diagrams are very, very important topics. Now, here a simply supported beam of total length 3 meters is taken, and from A to B it is 2 meters, and B to C overhang is 1 meter, and it is applied external force of uniformly distributed load of 1 kilonewtons per meter. This is equal to W. Now, let's delve into the problem. First, let us draw the shear force diagram by finding the shear force at various important points. This is the beam, and let us assume the reactions both are in the upward direction, and the UDL, and there is a overhang, and overhang is at point C. This is 2 meter, this is 1 meter, and we have to initially find out the support reactions. A is a pin joint, B is a roller joint, C is a free end. As far as the sigma Fy is equal to 0, sigma Fy is equal to 0, that says vertical loading is equal to the vertical downward loading is equal to the upward loading, upward forces, reaction forces rather. This is 1 kilonewton per meter. The downward load is 1 into 2 plus 3, 2 plus 1. This is the length. W into L is the total load that is acting downwards on the beam. And what is acting upwards? One is RA and another is RB. That is the directions which we have assumed. That implies RA plus RB is equal to 3. This is equation 1. For finding the support reactions. by taking the moments about the point A, by taking moments about A, about point A, it says this RB moment about A will be acting like this, and this UDL movement will be acting like this. Both are acting in the opposite directions. So that the UDL movement is equal to the reaction force B movement about A. What is the UDL movement? If a beam is there, beam is there, W and length is L, the moment is WL square by 2. Hence, this WL square by 2 is equal to RB into distance from A. That is, RB into 2 is equal to W is 1 and L square, total L, total UDL is acting on the beam. It's not part of AB. Total UDL. What is the total UDL? 1 into 5 meters. Not 5 meters, 3 meters. WL square by 2. That means RB is equal to 1 by 2 into 9 by 2. That is equal to 2.25 kilonewtons. This value is positive, hence whatever direction we have assumed that RB direction is same. Let us not change. If the value is negative, we have to change the assumed direction. The reaction force at B is 2.25 kilonewtons upwards. Then, that is the direction we have assumed previously. Now, RA plus RB is equal to 3. That implies RA is equal to 3 minus 2.25. That is equal to 0.75 kilonewtons. What is the direction assumed of RA? Initially, that is in the left hand side upwards. Hence, this value also direction need not be changed. It is come positive and it is 0.75 kilonewtons. Then, let's see, there is no reaction force. The shear force is 0 at free end. Now, as we move from point A, this is, let us say, X. This is X. At cross section X, the force will be, SFD will be, RA is acting upwards and the UDL is acting downwards, RA minus WX. W is the UDL. Load is equal to W into X, downwards. Hence, SFX, shear force X between 0 less than or equal to X less than or equal to 3. SFX is equal to, what is that SFX? Shear force at a point X is nothing but RA minus WX. W into X. At some point, RA is how much? 0.75 minus W is 1 into X. That means 0.75 minus X. Shear force at X distance. If you see, at a particular point, the shear force is becoming 0. Because we have to find out at important points where shear force, what is the value and what is the shape. Shear force X is equal to 0 at what X? That implies 0.75 minus X is equal to 0. That implies X is equal to 0.75 meters. At 0.75 meters, my shear force is becoming 0. That means SF, shear force at x is equal to 0, that is equal to 0.75 kilonewtons, and shear force at x is equal to 0.75, it is 0. Then shear force at x is equal to 2. What it is? That is equal to, for the first, that is 0 is less than or equal to, x is less than or equal to 2, not 3, sorry, it is 2. At x is equal to, what is the shear force value? Due to this reaction and UDL. Reaction and UDL only we are taking reaction at A. Reaction at A is 0.75. We have not considered the reaction at B yet. We have considered only reaction at A. Due to RA, 0.75 minus 1 into 2. That is 0.75 minus 2. What is its value? 1.25 kilonewtons. It is minus. That means somewhere shear force has changed its sign from positive to negative at 0.75 meters, and it went up to minus 1.25. That means for the first portion, when you consider, the shear force diagram will be like this. This is 0.75 due to reaction force, and at 0.75 at 0.75 meters, the shear force is 0, and at 2 meters, this is 2 meters, it is minus 1.25. This is plus, this is minus 1.2. And now, once you go beyond 3 or at 3, there is a reaction force also is acting. Reaction force is acting in this direction. This force is in this direction. Reaction force is in this direction, RB. When you add RB to minus 1.25, what happens? RB is 2.25. There will be a positive. RB is 2.25, and here it is minus 1.25. Not minus, when we put the arrow, it need not be. This is 2.25. That means net force will be 1.0. And at C, the value of the support, there is no support, hence shear force is 0. This is 1 meter. This is the shear force diagram. This is the shear force diagram. Now, here we have taken equation shear force for 0 less than or equal to x less than or equal to 2. Now, 2 less than or equal to x less than or equal to 3. In this, what we have to do? We have to add the reaction force also, because reaction force is upwards. What is that? 0.75 minus 0.75 minus 1 into x plus reaction force is 2.25 RB minus W into X minus 3. This is the shear force. One into X minus 2. Because this is up to 2 only. Up to 2 only. W into X. This equation is up to 2. We have to use, and afterwards we have to add this from X 2 is less than or equal to 3. This is how we have to calculate. And at X, SF at 0 is equal to 0.75. SF at 0.75 is equal to 0. SF at 2 is equal to, shear force at 2 is equal to this is not 3, I am getting confused unnecessarily every time. This is, I was doing some other, this W into X minus 2. At 2, what is the value? And you put 2 in this equation, you will get 0.75 minus W is 1 into 2 plus 2.25. That is equal to 3 minus 2, that is 1 kilonewton. Here it is what it is, 1 kilonewton. When you take the reaction force at B, when RB is considered, this minus 1.25 when RB is not considered. That means at 0.2 we will have RA only, and next immediately there only we have RB also. When RA only is considered, then negative value. When RB is also considered, there is a positive. This is what the shear force diagram. Now, let us go for the bending moment diagram. BMD. There is a principle called wherever, this can be a point of multiple choice question, wherever SFD is equal to 0, that implies BMD is equal to maximum. Here at X is equal to 0.75, SFD is equal to 0. That implies BMX at X is equal to 0.75 is maximum. Here, even though I have told you wherever SFD is equal to 0, BMD is maximum. The reason behind it is the calculus. As per calculus, for finding any variation value to be maximum, the differentiation d by dx of that particular value should be equal to 0. That is the principle. Here, d by dx of mx is equal to 0. What is the d by dx of mx? Please remember this. What is the d by dx of mx? D by dx of mx is equal to SFD. D by dx of mx is equal to SF at x. This is very important observation in finding the relation between a shear force and a bending moment. And for maximum values of bending moment, this d by dx of mx should be equal to 0. That is d by dx of mx, that shear force should be 0. For maximum bending moment, shear force should be 0. Shear force is 0 at what point in this example? At 0.75 meters. When shear force is 0, bending moment is maximum. That is the logic behind it. Now, next is, we have to find where bending moment is going to be 0. That means where bending moment is going to change its sign. What is the bending moment? Bending moment, when you integrate shear force, integration of shear force is equal to bending moment plus some constant of integration. These two things, please remember, bending moment is nothing but the integration of shear force, and shear force is nothing but the differentiation of the bending moment. These two are very important. Now, let's go for drawing the BMD. How BMD is drawn? How bending moment diagram is drawn? Bending moment at pin support is 0. Bending moment at left hand side pin support is equal to 0. And second thing, bending moment at free end is equal to 0. These are the two things we have to understand. And how bending moment is nothing but shear force into distance. If you integrate shear force, what is integration of shear force x dx? That is equal to bending moment plus C1. This is the equation which just now we have got. Now, what is the shear force at x between 0 less than or equal to x less than or equal to 2 in this region? What is the shear force? Shear force is nothing but 0.75 minus Wx. Do you agree? Shear force is equal to 0.75 minus Wx. Integral of shear force at x dx is equal to integral of 0.75 minus w is 1 into x dx. That is equal to integral of 0.75x minus 1 into x square by 2 plus some c1 when x is equal to 0 at x is equal to 0 bending moment is equal to 0. This is BMX. That implies c1 is equal to 0. Hence, bending moment at x from the left hand side for the reason 0 less than or equal to x less than or equal to 2. Bending moment is 0.75 x minus x square by 2. This is with the integration simply we have got. For example, if we don't want to use integration, in that case what we have to do? This is the beam, RA, this is RB, this is two meters, this is 3 meters, and RA is 0.75, this is 2.25, between RA and, this is 2 meters and that is 1 meter. I am still in the other problem which I was solving. In that only my mind is still there in 2 meters and 3 meters. 2 meter and 1 meter. When x is like this, we are not aware what is x. Bending moment. With this, due to RA, this is like this. Due to UDL, the moment is like this. This is the point x. Please visualize it. When RA is considered, UDL you don't consider. RA. When RA is acting like this is the x section, the moment will be like this. When UDL is taken into consideration, don't take RA, only UDL. This is the x. UDL is downwards and the movement will be like this. That is for UDL, direction of the movement. This is for RA. And RA is 0.75. And when the movement is in this direction, what it is positive. That means bending moment at any x is equal to RA into x. That is 0.75 into x. That is positive. And this is negative. This one. This one is negative. Minus W is the uniformly distributed load per meter into length. Length is x. And it is acting at the center of the x. That center of the x is x by 2. That is equal to 0.75 into x minus x square by 2 because W is 1. Either by integration or by this method you get the same answer. This is for 0 less than or equal to x less than or equal to 2. Now you have got the bending moment. At x is equal to 0, bending moment at x is equal to 0 will be, you put 0 in this equation, 0.75 into 0 minus 0 square by 2, that is equal to 0. Bending moment is equal to 0 at what point? Like shear force is equal to 0 at some point we have got. bending moment is equal to 0 at what point? That means 0.75x minus x square by 2 is equal to 0. That implies x square by 2 is equal to 0.75x. That implies x is equal to 2 into 0.75, that is equal to 1.50. At a distance of 1.50, bending moment is 0. Now what are the values we have got now? Bending moment at x is equal to 0 is equal to 0. Bending moment at 1.5, x is equal to 1.5. Just now we have got bending moment is equal to 0. And bending moment is maximum. Bending moment, what is the bending moment equation? 0.75x minus x square by 2. Then for maximum, d by dx of bending moment x is equal to 0. That should be 0. That means what is d by dx of this? D by dx of 0.75x minus x square by 2 is equal to 0. That implies 0.75 minus x square by 2 is 2x by 2 is equal to 0. That implies x is equal to 0.75 meter. That means at a distance of 0.75 meters, the differentiation of bending moment is equal to 0. That means bending moment is maximum. When d by dx of bmx is equal to 0. Where d by dx of bmx will be 0? When s of d is equal to 0. That means s of x is equal to 0. We have got the maximum value of bending moment. We have got the 0 points of the bending moment from 0 to 2. And another. At the point 2, what is the bending moment value? At x is equal to 2, bending moment x is equal to 2 is equal to 0.75 into 2 minus 1 into 1 into 2 square by 2. That is equal to 0.75 into 2 is 1.5 minus 4 by 2. That is equal to 2. 1.5 minus 2. That means at x is equal to 2, bending moment is equal to 1.50 minus 2.00, that is minus 0.50. This is the minimum bending moment because it is minus 0.5. At x is equal to, bending moment is minus 0.5. We have found the value of x at which bending moment is maximum, but we have not found bending moment maximum. Bending moment maximum at x is equal to 0.75 is equal to 0.75 into 0.75 minus 0.75 into 0.75 by 2. This value will be how much? Please calculate. 0.281. kilonewton meter. That means in between for the section bending moment at x is equal to 0 is equal to 0. Bending moment at x is equal to 1.5 is equal to 0. Bending moment at x is equal to 0.75 is equal to 0.281 kilonewton meter. And bending moment at x is equal to 2 is equal to minus 0.5. This is for the first portion. Let us draw the bending moment diagram for the first part. Second part we will take up now. It is A and this is B. This is one point at C, let me say, at 1.5 meters, bending moment is 0. And here at 0.75 meter, bending moment is maximum. That means it will go like this, it will come like this, it will. For the first part, this is 2 meters distance, this is 1.5 meters distance, this distance is 0.75 meters. For the first part, the maximum bending moment will be, this is positive, Bm maximum is equal to 0.281 plus 0.281. Here it is 0 at a distance of 1.5 meters and at a distance of 2 meters, the bending moment is how much? Minus 0.5. Now, the bending moment is 0 here, we know, at the free end. So, the bending moment diagram can be like this. And what will be its value? Between 2 meters to 1 meter, B and C. This is the shape of the bending moment diagram. And this 1 meter we have to calculate now. For calculating that for 1 meter, what is the shape and how it will be, that we will be doing it now. Bending moment at x is equal to 0.75x minus x square by 2. This is for the portion up to 2. And after 2, there is a reaction force. RB is coming here. This is RB. This RB will be acting like this. For the point up to C, that is positive. This is positive. RB into plus RB into, what is this? When it is x, this distance is x minus 1, x minus 2. Because we are taking, up to B we have taken care. After B it will be x minus 2. After B only we have to consider for RB. That is x minus 2. That is equal to 0.75x minus 0.5x square plus 2.25 into x minus 2. Now, Bm at x is equal to 3. That is equal to 0.75 into 3 minus 0.5 into 3 into 3 plus 2.25 into 3 minus 2. That is equal to 0.25 minus 0.5 into 9, that is 4.50 plus 2.25, that is equal to 0. That means whatever we have thought at the free end 0, bending moment is coming as 0. Ultimately, the final diagrams SFD and BMD are like this for a overhang. SFD and BMD. This is SFD. This is SFD and BMD is, you put the values I have calculated. You take it as a homework and do it. You put the values. This is the shape of the BMD. This is the shape of the SFD, this is the shape of the BMD. And in the objective type questions, they can ask what is the position of the point of bending moment 0 in addition to the supports. At supports, bending moment is already not supports, at the ends. Left hand side one end support, right hand side is free end. Except under ends. At what point on the beam the bending moment is 0? That question can come. Second, what is the value of the SFD where bending moment is 0? Third, what is the value of the maximum bending moment and at what point the maximum bending moment occurs? And what is the value of shear force when bending moment is maximum? What is the minimum bending moment value and what is the maximum bending moment value? Maximum bending moment is positive value, minimum bending moment is negative value with our sign convention. These are the different types of questions. And what is the shape of the bending moment? The shape of the bending moment curve, it cuts the beam at 3 points, at 2 end points and also in the at one particular x is equal to 1.5, it cuts the beam section. And under reaction RB, what are the values of SFD and BMD? SF, shear force and bending moment. That can also be asked. What is the shape of the shear force? It has three triangles. And shear force cuts the line of the beam at a distance of 0.75 meters. That also they can ask. What is the shear force diagram after the second support? After the second support, it is a positive triangle. Just before the second reaction, it is a negative triangle. Just after the first support, it is a positive triangle. Positive, negative, negative, positive are also important in addition to values. this is positive, this is negative, this is positive, this is positive, this is negative. And the sign convention is like this. Universal sign convention. Universally valid. Please don't deviate from it under any circumstances. It will be good for you. Other books, they may prefer other than this, opposite to this, the sign convention. But if you follow BC Punmiya or any other standard book like Timoshenko or any other standard book, you find this type of sign convention. Mechanics of Materials by Timoshenko or BC Punmiya, you find the values of this sign convention is followed like this. Now, with this I want to conclude this lecture. In the next lecture, we will take up the same problem for deflection. Deflection curve. How to calculate the deflection and how the deflection curve is going to look like. You please try yourself if you can. In the next class, I will take up this. The deflection curve looks like this. This is the deflection curve. At some one particular point, the deflection will be maximum. We have to find out this x. And here deflection is 0. Here at B deflection is 0. At A deflection is there. At C deflection is there. And what is this x? And what is the maximum deflection? Delta x maximum is equal to how much? These are the two things. It will be, there is an integration procedure which I will be following. I have already taught you area movement method. That also you can use. I will be using in the next class this integration method and I will be solving this. You please try to solve on your own and see my lecture. In the next class, I will be taking up this deflection in overhang. This is the curve, and with this I want to conclude this lecture. I am Ramchandra from Civil Mech Maths Concepts channel. Please subscribe to my channel. If there is a value addition to your knowledge, please share this video so that other aspirants also will get benefited. This lecture is for GATE SSC JE and also for UPSC ESC Engineering Services Examination. And UPSC Engineering Services, there is one question given in 2017. This is a point load here. This is a overhang. A, B, and this is C. This is L, and this is L by 2. And they have asked us to find out the deflection under point load C. At point C, under point load. Many people gone wrong, have seen somewhere, and the answer will be 1 by 27 PL cube by EI. That we will be considering afterwards. You please try this also. In 2017, in Engineering Services Examination, UPSC, this problem is given. You can refer to that problem and get the answer. The procedure will be same and it is asked for deflection after the next class. Deflection in overhangs. You can try. Otherwise, you can use my previous lectures and try for finding the deflection in overhang beam like this. Best of luck to everybody. Thank you for seeing my lecture. Thank you for listening to me. And please subscribe to my channel, Civil Mech Maths Concepts, and share the video so that others also get benefited from my videos. And I have given sufficient input regarding the overhangs and the shear force diagram and bending moment diagram in this lecture. I will be taking up the deflections in the next class. Thank you. Best of luck.